what about in FDD conditions, sir? Both PUSCH DMRS and PDSCH DMRS should be used, sir. Always.
Yes. So even in TED, Vijay, even in TED, DMRS is always there for both PDSCH and PUSCH. Okay. See, remember, there are multiple reference pilots. One is the DMRS, and the other is the CSIRS on the downlink and the SRS on the uplink. Okay. So the CSIRS and the SRS are used for channel quality estimation. I mean, you don't generally get fine channel estimates with SRS and CSIRS. Okay, you get coarse channel estimates. You understand which direction the UVE is. You understand the quality of the channel and other things. Okay. So finally, and the thing is, the pre-coders that you use are also not applied on the SRS and CSIRS. Okay. So DMRS is the pilot, are the pilots which are tied in very much too much with the data. Okay, they are pre-coded exactly like the data is done. Okay, they have higher densities. Okay, so the DMRS is generally present. Without DMRS, you cannot be able to get any good bit error rate. Okay. SRS in the TED is used as, for example, when you have TED systems, the uplink SRS is used to understand the downlink precoder. Okay. In FDD systems, CSIRS is used in the downlink and SRS is used in the uplink. Both of them have to be used. Okay.
Okay. Yes, sir.
DMRS has to be always there. Without DMRS, you cannot do fine. See, like how you did channel estimation in the OFDM assignment. Now, what you developed, you divided by the pilots and found out the channel estimate. That part can only be done with DMRS. You generally don't do that with SRS and CSIRS. Okay, SRS and CSIRS are mainly to understand the pre-coders. Of course, you can also use DMRS for that. There's no question. I mean, but unprecoded SRS and unprecoded CSIRS will be used for CSI purposes, channel state information purposes.
Okay? Thank you, sir.
But saying that there's no, I mean, the spec does not restrict to use anything. I mean, the spec says it's all there, but this is what people generally do. You can always use CSIRS to do these things also. There's nothing that prevents you from doing that. Okay? Good. Okay, so let's start today's class. I actually, by the way, I shared a nice paper with you today. I mean, this is something that's written by people from multiple companies. In Oreo, the physical downlink control channel for 5G and R. If you have time, just read it. It's a little bit older paper. I mean, things have changed a little bit, but more or less it gives a good idea of what things are. Okay. Just to give you some brief idea of the picture. So, I mean, we have done this. We have done this. There are multiple core sets. Core sets have physical resource block, what we call as REG. Okay, resource element group. Sorry, REG is correct. Okay, which we call REGs. And then, so this is the slide this is the picture I want to emphasize now on. So core sets are physical resources.
Your screen is not visible.
Oh, sorry. Really sorry. Not a matter. Sorry, thanks for that. Okay, you can see my screen now. Can you see my screen?
Not yet. No, sir.
It is coming blank, sir. It's coming blank.
It's coming blank. Is it coming now?
No, it is still blank, sir. Screen is there, but it's blank.
Yeah, now okay, sir.
It has started coming, sir.
Can you see my picture? The picture figure 3? Okay.
Some
Okay,
yes,
so,
pictures are there.
Okay, good. So this is what we were looking at. So we saw the water core sets. Okay, core sets are actual physical locations in the time frequency grid. Okay,
but that is not able to we see it. How it has come.
Now, okay, perfect.
Is it not? Okay, you can see the core sets now. Okay. So this core sets, I mean, we saw that are the physical resources. These are the physical resources, okay? And we see that multiple core sets can be there on, in the bandwidth part. Okay, so for example, this was core set 0, and this was other, 1, 2, 3, 4, 5, 6 other core sets, UV specific core sets. Okay. Okay, so and we saw that the core sets are indexed by, essentially the fundamental unit is the resource element group. Okay, REG group, resource element group, which is called as REG. Okay. So then REG, what is an REG? We saw all those things. Okay. So now let's look at the hierarchy a bit. Okay. So we have the core sets. Core sets have REs. As of this REs and REG bundle.
Hello.
So you are inaudible, sir, now.
Hello, you are not audible, sir.
Am I audible? Hello. Am I audible?
Now you are audible, sir.
Sorry, am I audible?
Now you are audible.
Sorry, sir. There seems to be some issue. Now you can see my screen. I was talking and now can you see the screen? Figure 3.
Well, that page number 3, that BWP core set 0, that screen is able to see.
It is
Okay,
figure
I'm just
2.
going to stop
Now
sharing
figure
my
3.
screen,
Yeah.
reshare it
Figure 3
again.
has
There
come
seems
and
to be
gone.
some issue. Just hold on. Just 1 minute. I'm going to reshare it. I think there seems to be some lag in the whole thing. I don't know why that is happening. You can see figure 3 now, na?
Yes, now, yes.
Yeah. Okay. So let's understand this figure. This kind of an interesting figure. Okay. So you have the core set. Okay, you have the core set, which is some time frequency resources. Okay, they are REGs. There are multiple REGs in this. Okay, a set of these REGs form the REG bundle. Okay, so here what did you do? So this is an interleaved CCE to REG mapping. Okay, so essentially what happens? An REG, a 0th REG will be here. First REG will be somewhere. You can see my cursor now, somewhere here, and so on and so forth. 17 REG may be somewhere here. Okay, this is interleaved thing. Okay, so these REGs are mapped to CCEs. Yes, that's what we saw. CCs are how CCs are mapped to REGs. Yesterday we saw both interleaved and non-interleaved. We saw the examples. Okay, that's good. Okay? So these are actual physical resources. Okay, so now what happens? See, by the way, at any point, if I'm not audible or anything, you please also WhatsApp me. I'm here. I'm keeping this thing also in case I can't, because I can't see the screen. So what happens now? You have PDCCH and we have PDCCH candidates. Okay, so PDCCH candidates means what? These are the actual PDCCH data that you want to, multiple formats of data that you want to transmit. Okay, so what do? You take this PDCCH candidate, you choose a particular aggregation level based on how much far the user is, how much coding you want to apply, you choose an aggregation level. Okay, so now the PDCCH candidates have to be mapped to the CCs. Okay. Okay, so now let us understand this carefully. Okay, so finally CCEs are while the actual physical resources are REs and other things, finally when we talk about the physical control channel, we talk about only CCEs. Okay, so this is what is a core set. Core set is the possible locations that a UV will get its control channel information from information channel. Okay, core set doesn't mean that entire core set will be full of data that the UV should decode. Okay, it is a possible locations. Okay, this is a possible locations. Okay, suppose now what happens? You choose an aggregation level 2. Suppose you want to send an aggregation level data to. Okay. Aggregation level data 2 means each PDCCH will take only 2 CCs. That's what aggregation level 2 means. Okay, that's what we saw also. Okay, so here so essentially what can happen, they can put these two things, either they can start at 0, they can start at 1, they can start at 2, 3, 4, 5, 6, and so on and so forth. Okay, but once you do that, what happens? The UV will have to blindly search across all the CCEs to understand what is the data that it's transmitted. It does not even know at that point what is the aggregation level. Okay, so it has to first, it will start doing aggregation level 4, then aggregation level 2, then aggregation level 1, and somewhere it decodes. Okay, so instead of that, what they did was they said that if you are using aggregation level 2, then your data, the PDCCH candidate can only start at particular indices. For example, in this particular case, they said that it can start only at index 0 and index 8 and some other things later. Okay, whatever they showed here, they show. Okay, similarly, when you do aggregation level 1, if you send aggregation level 1, it will start only at 0, 4, 9, 13. Okay, aggregation level 4, there can be only one candidate in this core set. That is a core set at CC number 0. Okay, so these are the, this is an example. So these are the possible positions in which your PDCCH can start with these different aggregation levels. So what does the UV do? UV will monitor only these locations. So it will monitor the CC index 0 for aggregation level 4, in aggregation level 2, aggregation level 1. It will monitor the starting index number 4 for aggregation level 1. Index 8, it will monitor for aggregation level 2. Index 9, it will monitor for aggregation level 1. Index 13, it will monitor for aggregation level 1. Okay, so these are the only things it will monitor. It will not monitor, it will not go on blindly decoding every CCE and then say, okay, should I decode aggregation level 4, aggregation level 2, and other things. Okay, so this is what are called search spaces. Okay, so the search space for aggregation level 2 is the CCE that starts at 0 and the CCE that starts at 8. The search space for aggregation level 1 in this core set is the CCE that starts at 0, 4, 9, and 13. For aggregation level 4, it is the CCE that starts at 0. Is this clear? Is this idea clear?
But still searches for all aggregation level indexes, no, sir?
It has to search for all aggregation levels. Okay, so in this particular case, how many does it search? How many blind decodings does the UV do? It will do 1, 2, 3, 4, 5, 6, 7. 7 blind decodings it has to do. Okay, by the way, one more thing that you should remember. Okay, the same bandwidth part can be shared by multiple users. So the same core set can be applicable for multiple users. Okay, just because the base station sends a data at aggregation level 2 at 8 does not mean it's for all the UVs. Now only for some UVs it is. So it has to decode all that, get to the CRC and check the RNTA whether it belongs to it or not. You understood that?
No, okay, sir. Can you please repeat, sir? I didn't.
Okay. See, this is a core set. Okay. See, this core set has a search space. Fine. So there are some UV search. So if you look at can you look at this picture? Can you look at figure 2 now? Is figure 2 visible?
Yes, sir.
Okay. Now let's understand this. Okay. So this is a bandwidth part. This is a bandwidth part of some 48 RB. This is just an example. Okay. So the same bandwidth part, multiple UVs can be given the same bandwidth part. Now, there's nothing that prevents you. You cannot say each bandwidth part is unique to a particular UV. Multiple UVs can have different bandwidth parts. Can have similar bandwidth parts. Agreed, all of you? Okay. So when they define the bandwidth part, they can define the same core sets can be defined for multiple UVs. Okay, they are UV specific, but they're the same physical. They are the same. What do you say? The same physical resources that are registered for all the UVs. Okay, did you understand this? Vijay, is this clear?
Yes, sir. Yes, sir.
Okay. Okay, so the same core set space is shared by all the UVs. Okay, while it's called a UV specific thing, it does not mean that all the resources are allocated for that UV. Okay, it does not mean that. Okay, now let's come back to this picture. Okay, so for this UV, this can be the search space. For the other UV, there can be different search space inside this. Okay, I'll show you some more. I'll show you a picture. I'll show you a picture later. Okay. So what will happen for the next UV? The aggregation level 4 can start at this point. For the third UV, the aggregation level can start at this point at 10. Okay. For this UV, this is the search space. For the second UV, which is sharing the same core set, the search space can be a little bit different. For example, for aggregation level 1, for the second UV, it can be CCE1, CCE5, CCE10, CCE14. Okay.
Means it aligns with core set position, starting positions.
It aligns with core. I mean, it can be, essentially, core sets are, finally, core set is the fundamental unit. Okay. Core set has REs and other things. Core sets are mapped to CCEs. Yes. The aggregation levels are defined in terms of CCE indices. Okay. So there's an abstraction. So let me just share my screen once. Okay, I can't share my screen because of my iPad. Okay. So see, one thing you should remember, Vijay, is the same core set can be shared by multiple UVs. Yes. So finally, we have abstracted out all the REs and other things and came to CCE. CCE to REG, CCE to RE mapping, it's unique. It's defined in a certain way. Okay. CCE to RE mapping, CCE to REGs and REGs to RE mapping is defined. Okay. So now what might happen? Multiple UVs might share the same space, might share the same core set space, might share the same search spaces also, might share or might not share. It's up to how we configure them. If they share the same search space, for example, two UVs are sharing the same search space. Okay. So, and they're sharing, of course, the same core set also, that means. Then what might happen? A UV, for example, the base station sent the control information, let's focus on aggregation level 2. Okay. The base station sent information to UV2 starting at 0 and UV1 starting at 8. Okay. So now what will the UVs do? The UVs will first try to solve aggregation level 4. They will not find anything. Okay. Then they'll come to aggregation level 2. Okay. UV1 will decode both these things. UV2 also will decode both these things. It will only decode these two and these two. Okay. At that point, what will happen? UV1 will look at the CRC of this and will fail. Okay, for UV2, the CRC of this will pass. The candidate that is starting at 0. Okay. On the other hand, for the candidate that's starting at 8, for UV1 will pass and UV2 it will fail. Okay. So that's how they decode that. Is it a little bit clear, Vijay?
Yeah, it is clear, sir. But you said, sir, earlier for UV2, AL is equal to 2 can start from CCE index 3.
It can also start at CC index 3.
But how, if core set is same for both the UVs, then how actually specs identify this? It should be 0 and it should be 3 like that.
Yeah. Okay, I will tell you that. That's a very good question. That's a very good question. So what will happen is I will tell you that part. Okay. You can see my other document 38213.
Yes, sir.
I'll show you the formula for it. Okay. See, so essentially for a search space, yes, that is allocated to in a core set P. Okay, the CC indices for an aggregation level L are given by this big formula. Okay, essentially what they are doing is they're partitioning this core set. I mean, they're telling that in a given core set, how is the mapping from a search space S to the CCs. Okay, so there's a big formula. Yes. So this formula depends on a lot of parameters, including the RNTIs, user-specific RNTIs and other things. Okay. So for example, for group-specific search spaces, this will be a common RNTI. For a user-specific RNTI, so essentially you can see that how you put the search spaces is a complicated formula that is given by that's a combination of what is the search space. I mean, what is the index of the search space? What is the index of the UV? I mean, what is the core set number, core set P, and all those things. Okay. So they compute using this formula. And the base station also puts your data in only these particular search spaces for that particular UV, for a UV specific search space. Okay. Okay. So
Yes, sir.
I'll show you a few more things. Just hold on. Did I put this? Okay, I'll put this. Okay. So this is something I did not tell you. Okay. So I mean, we did not go through this in carefully. You can see my core set IE. Na? So every core set has its core set ID. Okay. So every core set has something called a core set ID. Of course, there are other parameters which we saw. We saw frequency, domain, resource, duration, and all the interleave, non-interleave. But a core set is also identified by control resource set ID. Okay. Control resource set ID is nothing but some integer. Okay. That identifies what is the core set number. Okay. Then let's go into search space. I'm just going to maximize this for a minute. Okay. So this is a search space. So what happens before you decode this control information, all these RRC parameters will be sent. Yeah, these RRC parameters will be sent in either SIV1 messages, or when you do PRATs, you send a lot of RRC messages. Okay. So when you do that, the search space corresponding to the control resource ID is defined by this formula called search space. It will tell you what is the aggregation level that is used. Okay. What is the aggregation level? How many number of candidates of this aggregation level are there in that search space? 2, 4, 8, 16 aggregation levels. What are the different formats that are there in these aggregation levels? Okay. All these things are specified to the UV. Is it clear?
Yes, sir.
Okay. So these IEs also go there. These IEs also go there. And once, so essentially so at the, before the UV decodes the DCI formats, it knows that this search space corresponds to this particular aggregation. I mean, these are the aggregation levels that are there, and this aggregation level corresponds to these particular DCI formats. Okay. So let's look at this. So this is an example from LTE, but something similar. I mean, we can see this. Okay. Now let's look at this. Okay, this is a little bit different from NR, but that's okay. I mean, this is just to understand the concept. Okay, you can see this slide now.
Yes, sir.
Okay, so let's look at the top slide. Top picture, sorry, top slide, the top picture. There are two terminals, terminal A, terminal B. Okay, so you can see this is the same physical resources, what we think of as core set now. Okay. But you can see, what you can see is, I mean, there are different aggregation levels, have different search space. There's something called common search space. There's a UV specific search space. I mean, this is a little bit different from NR, but just to give an idea. And this on the top is the 61, 2, 3, 4, 5, 6, 8 aggregation level. Next is the 4 aggregation level, 2 aggregation level, 1 aggregation level. Okay. So the terminal A search space is given by this, highlighted in this red. Okay. Similarly, terminal B, which is sharing the same core set or the same resources, has one more search space. Okay. So for example, if you are sending, if terminal B you have selected, you can let me just make it full screen so that I can use my. Okay. So for terminal B you have selected aggregation level 4, and you have selected this this point for base station is transmitting in 16, starting at 16. Okay. So at terminal A, you want to send aggregation level 2. Then you will not be able to transmit here. This point is out. You will be able to, you can transmit any of this other 1, 2, 3, 4, 5. 16 is out because 16 you are using for this. Or you can actually use 16 for terminal A and 20 for terminal B. Agreed? So now what will the what will the UVs do? The UVs will only search these spaces. And if you send 16 for terminal A and 20 for terminal B, 20, I mean 4 aggregation level for terminal B, and 16 you send aggregation level 2 for terminal A. The terminal A will first start searching for this 8 aggregation level, will not find anything. Then it will start searching for the 4 aggregation level, will not find it. In its own search space, it will search. And it will start searching for aggregation level 2 here, and 16 it will find. Okay. And similarly for terminal B, what will it do? It will start searching at 20. It will start searching everything like this, and it will start searching 4, and it will 16. It will search, but it will not find an aggregation level 4. It will do 20, and it will find. Okay. So suppose terminal A and terminal B want to both send aggregation level 2. Then what will happen? You can choose any of this from this point and any from this point. Of course, they should not collide. Okay. So you can choose, for example, 8 here and 6 here. Okay. Then what will happen? Terminal A will decode both 6 and 8. But A for 8, CRC will fail. Okay. Terminal B will decode both 6 and 8. But 6, its CRC will fail, but 8, it will succeed. Okay. That's how they decode. Is this clear?
Yes, sir.
Okay. Good. Good. So I want to tell a very important point at this thing. Okay. This juncture. Okay. So there's always this question: how many UVs does a base station support? Okay, there's always this fundamental question on how many UVs does a base station support. So theoretically, you can allocate when you're doing downlink allocation or something, you can allocate very, very few resources to UV. You can able to support hundreds of UVs. Okay. But the problem is always the search spaces. Okay. Because you cannot put so many chord sets for all the UVs, disjoint chord sets. So you will share chord sets below. At least if you think about LTE or thing, which is a little bit more clear, you will share the same chord set space. Okay. And if you configure NR also, the way people are configuring NR is they allocate the first two symbols for chord sets. Okay. Now the main problem is the search space packing. Okay. So you understand now. So the number of, for example, the number of two terminal A, terminal B are there now. So the number of aggregation levels that you can pack is limited because these search spaces has to be shared across multiple aggregation levels and the multiple terminals, multiple UVs. Okay. So if you use an aggregation level 4 for one terminal, which is far away, then it restricts the usage of aggregation level 1, aggregation level 2 for some other user. Okay. So effectively what happens is the number of users you can serve in a slot by a base station actually more or less depends on the DCI packing, what they call that. This is what is also called the DCI packing, Does it, is this clear?
Yes, sir.
Okay. So see, this is a very, very difficult problem. Now, when the base station, at the base station, you have to make this call. What are the information that you have? You know, for one user that the channel is bad. Okay, so the channel is bad. So what do? You choose a higher aggregation level because you want to use a lower coding rate. Okay. And there are other 5 users who are okay. Okay, so you want to use aggregation level 2 for them. And there are 3-4 users whose channel is very, very good and they have only short information. You want to use an aggregation level 1. Okay. So now you have to solve this problem of packing all this DCI information in the same chord sets, in the same 1 or 2 chord sets. Actually, it's a very, very difficult problem. It's actually a packing problem, which is an NP hard problem. Okay, so there are lots of heuristics that people use to solve this kind of a problem. This solving this aggregation level, packing this control information. Okay, it's like a pretty interesting problem also. Those of you who are interested should think about this problem a bit. Okay. So more or less, this determines how many users are served per slot in a cell. Okay, so if you are able to do very good packing because of your algorithms or something, you'll be able to pack more users. If not, if you are doing some lousy packing, you'll be able to serve only a fewer number of users. Okay, is this clear? Any questions on this?
It is true for LTE also, sir. The
same thing. See, here they said chord sets and other things. In LTE, the chord set used to be the entire first 2 symbols of the entire bandwidth. Okay, that's the only difference.
Yes.
Here, they introduce the notion of chord set because there's a notion of bandwidth parts and other things. They don't want to generally broadcast information all around. Okay. So I hope you understood the notion of what is a chord set, what is a resource element group, what is a CCE, and what is a search space. Okay. So finally, CCEs are the things in which you map the control information. CCs are a higher level abstraction. They have RAG bundles, RAGs, and RAs finally. Okay. Okay. With this, now let's go on to the next part of the control channel. Okay. So finally, until now, what we learned was we learned how to, given a control channel, we learned how to map it into chord sets and we learned how to map into search space. So by the way, I skipped all these formulas and other things, which slots it is and other things. Okay. this goes deep into the spec and other things which we don't require. I mean, if you are interested, please read the slides and I'll tell you it is there in which document it's there. It's 38313. Okay, the control document. Okay, this is a document that is there. It's called the 5 control layer procedures. This is the document that has completely about physical layer control procedures for control. So you should go to section 10 and look at UV procedure for determining physical downlink control channel assignment. Okay, there's a huge chapter on this, which also explains you the formula and other things. Okay, I mean, there's no, I mean, yeah, I mean, it goes into more nuts and bolts of things, which we don't require at this point. Okay. So now let us look at what actually goes into the PDCCH candidates. Okay, these are called the DCI formats. Okay, so finally, we should, if you understand the DCI formats, so the DCI formats have all the information that is required to schedule users, inform about your MCQs and MCIs and other things. Okay, so we'll go through this a little bit. Okay, what are the different formats that are there, and what format serves what purpose? Okay, excuse me. Okay. So as I said, DCI, I mean, we'll also similarly do the uplink control information, but first let's focus on the DCI first. Okay. So DCI has both downlink and uplink scheduling assignments. Okay. So finally, it's a base station which controls what has to be transferred in the downlink and what is transferred in the uplink. Okay. So both the uplink and the downlink scheduling assignments are provided by DCI. There is also hybrid ARQ. This is what is hybrid ARQ. Hybrid ARQ means essentially whether it takes care of ACK, NAC, and also retransmission. You have to inform about retransmission. It will also inform about power control. Okay. So there's one more thing that has been introduced in 5GNR. You can change the TDD structure, uplink, downlink structure of a UV based on the DCI format. Okay. Very, very fine control of that is also there in the DCI formats. Okay. So effectively, you can use the DCI formats to do full duplex communication also if you really want to. Okay. The multiple DCI formats. Okay, so the DCI format Z00. Okay, so there. See, let's focus on the first 4 formats first, and then we'll do the second formats. 2 formats. Format 2s are more or about common information. 0001, 1011 are called the. I mean, are for the more UV specific. Okay. Okay. So you see, let's look at 00. What is 01? Okay, so what is 00 and what is 01? 00 is called the short format or the default format for uplink scheduling, PUSCH scheduling. 01 is a long format for PUSCH scheduling. 10 is the default of the short format, and 11 is the long format. Okay. So 00 and 01 corresponds to things starting with 0 corresponds to the uplink scheduling. The things starting with 1 correspond to the downlink scheduling. Okay. The second thing, if it is 0, it means it's a shorter DCI format, and 1 means it's a longer DCI format. Okay, same thing holds for other things. Okay, we will start. Let's understand what are the Let's understand what are the things that are there in this DCI formats. I will also actually show you the spec also a bit, and then we'll go ahead with the things. Okay, so DCI format 10 and DCI format 11. There are 2 formats. Okay, so let's see the spec once. Let's see the spec and understand where this is. Sorry. So these DCI formats are there in the 38212. Okay. So if you go to downlink control information, there's something called DCI formats. DCI formats for PDSCH, okay, which is format 10 and format 11. Okay. So this tells you exactly what are the bits that are there. What is indexed in this. So first let's go through the slides, and then we will go through one of this, at least DCI format 10 and DCI format 11. Okay. So DCI format 10 is called the short format. Okay. Let's understand what are there in this. So any questions before I proceed? Hello, am I audible?
Yes, sir.
Okay. So let's go through this slide and then we'll go in detail on the 1.0 format at least. And 1.1 format, I will leave it as an exercise for you. Okay. So what is the DCI format, downlink control format 1.0 and format 1.1? They do downlink scheduling. Okay. So essentially what is meant by downlink scheduling? It will tell which UVs are scheduled. Okay. And what is the frequency time allocation for that particular UV along with the MCS. Okay, so what is there? Of course, there's one bit called as format identifier, which tells you whether it's a 1.0 format or a 1.1 format. Okay, resource allocation, essentially, it does the frequency domain resource allocation. It does the time domain resource allocation. We haven't done the resource allocation and resource assignments yet. It also has interleaving, non-interleaving mode, which is called the VRB PRB mapping. It will tell you whether that is there. Okay. It will tell you for each transport block, if there are two transport, for format 1.0, there's always only one transport block. It tells you what is the MCS, what is the RB. RB is the redundancy version. We saw this redundancy version when we did the circular buffer, whether it's the first transmission, second transmission, third transmission. NDI means new data indicator, whether it's new data or it's old data corresponding to the previous transmissions. It will also identify what is the hybrid ARQ process. It will tell you which part of hybrid ARQ. Hybrid ARQ allows for 16 processes in 5GNR, so it will tell you which is the process number. If there's multiple antennas, it will tell you what is the antenna ports for which this in which you are scheduled. It will tell you the other things also. We'll look at this later. I also tell you information about your uplink, downlink power uplink power control also it will do. Okay, so let's just go through this format, one format at least. Let's understand this, how it looks. Okay. So DCI format 1.0 is called the DCI format 1.0 is called the basic format, basic downlink format. Okay. It's also called the fallback format. So essentially, when is DCI format 1.0 used is DCI format when you initially start your communication, you actually, you don't know too much about your MIMO setups and other things. So you actually do, this is the fallback format in which they use. This is a very short format. Okay. If you don't have MIMO also, you can use format 1.0. You can also every time use format 1.0, but format 1.0 is generally used when you, for example, when your connection is served because your coverage is deteriorating or something, your connection is served. Then when you restart, automatically the basic format you will start the DCI is format 1.0. First time the base station talks to you, it always talks to you in format 1.0. Again, format 1.0 does not have MIMO. Okay, format 1.0 does not support MIMO. It's just a basic CISO support. Okay, is this clear? Let's look at understand this. Okay, maybe this is not a very okay. Let's try this out. Let's try this out. It says, I'll zoom it a bit so that you can read, all of you. So the following information is transmitted by means of DCI format 1.0. So essentially, how you use the DCI format 1.0 depends on to whom it is intended. Okay, so DCI format 1.0 has different formats when you transmit it for random access response versus when you transmit it for a UE specific thing. Okay, so so when you read this spec, it will tell you what is the format when the CRC is scrambled by different formats. For example, when CRC is scrambled by CRNTI or CSRNTI or MCSR CRNTI, the following information is transmitted. Okay. Otherwise, when you are transmitting with PRNTI, different information. Okay. So similarly, when you're transmitting for RARNTI, okay. So RARNTI is what? When you're doing random access response, when the base station is responding with the first DCI message after random access patch, this is the following information that is transmitted for when you're transmitting. So if you look at this, what it says is the frequency domain resource assignment is done. So essentially, the first time the UE has logged on, so it's giving it uplink, downlink resources. Okay, it says these are the frequency domain resource assignment. It's saying what are the resource elements that are given to you. Time domain resource elements, essentially what are the OFDM symbols that are allocated to you. What is the modulation and coding scheme that is used. Okay, and some other information. Very simple, very straightforward thing that is done. Okay. On the other hand, when you're doing with complete, I mean, it's a full-fledged UV, that is CRNTI, it has a little bit more. Okay. What I'm going to do is I'm going to make a table of, I may have a table of this somewhere. Wait. Okay. I'll make a table of this. And in the next class, tomorrow's class, what we'll do is we'll go through these formats, format 10, format 11 in more detail, and try to close it up. I mean, we'll also finish 0, 1 and 0, 0, 0 and 0, 1 formats in the next class. Okay. Any question? So meanwhile, what I would suggest you to do is all of you please at least try to read some part of this paper so that your ideas about chord sets and other things become clear. Okay. I mean, at least the initial part of the paper you can read. You will understand this whole paper. Is this fine?
Okay.
So I'm
So
going to
tomorrow
stop now.
class also at 9 a.m. only?
Yeah, we'll do at 9 a.m. So is 9 a.m. comfortable for everyone?
Yes, sir. Yes, sir.
Then we'll do at 9 a.m. sir. It's good. It's good then.